All right, let's talk about something absolutely fundamental in engineering mechanics, the cross product. Now, I know it can sound a bit abstract, but trust me, this is the key to understanding how forces actually create rotation. It's a tool you're going to use all the time.
Okay, let's just dive right in with a question you've probably never thought to ask. You grab a wrench, you pull on it, but why does the bolt turn in a direction that's completely different, totally perpendicular, to both the wrench handle and your hand? That little bit of everyday magic is exactly what we're going to unravel today.
So here's our game plan. We'll start with that wrench, then we'll formally introduce the cross product and what makes it tick. We'll cover its unique rules, how to actually calculate it, and then bring it all home by applying it to the moment of a force. Let's get into it. Section 1, a wrench's turning effect. We're taking something you've held in your hand a million times and turning it into a really powerful engineering concept. So let's really picture that wrench. In the world of physics, that handle isn't just a handle, it's what we call a position vector. We'll label it R. And the pull from your hand, that's our force vector, which we'll call F. And the turning itself? Well, that's the torque, or what engineers usually call the moment. Okay, so we have this physical action. Now let's give it a proper name. Section 2, introducing the cross product. This is literally the mathematical language designed to describe that turning effect. So what in the world is the cross product? It's a really special kind of vector multiplication. See, when you cross two vectors, say A and B, you don't just get a number, you get a whole new vector C. And the coolest part is that C is always perpendicular to the first two. And this is why we care. This is its whole job in mechanics. The cross product is the essential tool we use to calculate that turning effect, that moment of a force, and it's perfectly built for describing things that happen in 3D space. Section 3, magnitude and direction. So if the cross product gives us a new vector, what do we need to know about it? Well, it really just boils down to two simple questions. How much turning is happening and which way is it going? The how much is the magnitude. The formula is C equals A times B times the sine of theta, the angle between them. And this little formula explains so much. It's the reason you get the most turning power when you pull at a perfect 90-degree angle to the wrench, because the sine of 90 degrees is 1, its absolute maximum value. Now for the direction. And for this, you're going to need your right hand. No, seriously, go ahead and hold it up. First thing, point your fingers in the direction of that first vector, A. Just think of it as the wrench handle. Got it? Okay, now you're going to curl your fingers toward the direction of the second vector, B. That's the force you're applying. And boom, there it is. Your thumb is now pointing in the direction of the new vector, C. That's the direction the bolt is going to move, perfectly perpendicular to the handle and your force. It's so simple, almost like a little trick, but it is incredibly powerful and works every time. All right, on to section 4, the rules of operation. Now, the cross product plays by its own set of rules, its own unique algebra, and it's a little different from the normal math you're used to. Okay, this is probably the single most important rule to remember. Order matters a lot. In regular math, 2 times 3 is the same as 3 times 2, right? Not here. A cross B gives you vector C. Let's say that's tightening the bolt. If you flip the order to B cross A, you get negative C. And that's not just a math quirk, it's reality. You've literally reversed the operation. Now you're loosening the bolt. But don't worry, not everything is backwards. The cross product still follows some familiar rules you already know, like multiplication by a scalar and the good old distributive law. So we can still manipulate our equations in some predictable ways. Now, let's get down to business. How do we actually calculate this stuff? Section 5, calculating with vectors. This is the engineer's blueprint for putting the cross product to work. So in 3D space, we have our good old friends I, J, and K for the X, Y, and Z axes. The right-hand rule helps us here too. A really neat trick is to picture I, J, and K in a circle. If you cross them going counterclockwise, like I cross J, you get the next one in line, which is K. But if you go clockwise, you get a negative result. Oh, and remember, if you cross any vector with itself, like I cross I, the answer is always 0. But let's be real, trying to remember all those IJK rules for a complex vector, that's just asking for a mistake. That's why engineers use a much more powerful and systematic tool, the determinant. You just set up a 3x3 matrix like you see here, with IJK on top and your vector components below. This method is your best friend. It gives you the right answer every single time. And that brings us right back to where we started, our final section, the moment of a force. This is the number one reason we use the cross product, and it's the final answer to our question about the wrench. And here it is, the payoff, the moment, which we call M, is simply the position vector R crossed with the force vector F. M equals R cross F. That one beautiful, elegant equation captures the entire physical action of making something turn. Now, here's a super useful pro tip for you engineers, the principle of transmissibility. It sounds complicated, but it just means you can think of a force vector as a sliding vector. When you're calculating a moment, your position vector R can point to any spot along that force's line of action, and you will get the exact same answer. It gives you a ton of flexibility when you're setting up a problem. So let's recap the absolute must-knows. 1. The cross product creates a new vector that's perpendicular to the original 2. 2. We find its direction with the right-hand rule. 3. Its main job in our world is calculating the moment of a force with M equals R times F. And 4, I'll say it again because it's that important. Order matters. We've just unlocked the fundamental math behind rotation, so I'll leave you with this to think about. Now that you can see and calculate moments, what other invisible forces all around you in the world of engineering can you finally start to understand?